Today, lesson 13C, the topic today is angle similarity. So we've been spending some time on angle relationships, and with those angle relationships, which most of the time stem from either parallel lines or some sort of picture where we may have had a triangle in it, or maybe even a quadrilateral, today we return to this idea of similarity. Because before today, in order to determine if two shapes were similar to each other, the corresponding sides had to be proportional. Well, sometimes there's a faster way of telling whether two shapes are similar or not, and that comes from this idea of something called angle similarity. So that's where we deal with the situation we're dealing with today deals with two shapes and checking for that. All right, so complete the following statement. If two triangles have corresponding angles that are the same measure, then one triangle can be mapped to the other using, and this goes back to things we've been talking about over the last unit, they can be mapped to the other using rigid motions and dilations. Therefore, the triangles are similar to each other. When we're restricted to rigid motions, remember that leads to congruency or congruent shapes. But as soon as we incorporate dilations, now we have similar shapes. So I have a question for you, and that's this. Do all three pairs of corresponding angles have to be congruent in order to say that the two triangles are similar to each other? What if two pairs of corresponding angles are congruent? What if only two pairs of corresponding angles are congruent? And would the triangles still be similar? Why or why not? So we said before that similar shapes, the corresponding sides were proportional, and we also said that all the corresponding angles are congruent to each other. So the answer to that first question is yes. But what if I have these two triangles right here, and what if I only am given two angles? Is that enough for me to say that these triangles are still similar to each other? I want you to think about that for a second. And I want you to have a quick conversation with your shoulder partner. We've got a lot of people missing today, but if your shoulder partner's not here, just talk with somebody around you. The question once again is that enough information for me to determine that these two triangles are still similar? Go. If I take that triangle and I find the third angle, obviously the third angle in each one will be congruent to each other, but not just that, because sometimes the triangles don't look like this sitting next to each other. Sometimes we have a situation like this, or sometimes like this, or sometimes like this, or sometimes like this, or like this. They're still similar to each other. The point that I'm trying to make here is that if we know two of the three angles are congruent to each other, the corresponding angles, that means they're still similar because of the fact that when I dilate one, they map on top of each other. So if I know two angles are congruent, that's called the angle similarity property. And we automatically will know that the two triangles are similar to each other. So this is kind of what today is all about. We're trying to determine if two triangles are similar to each other without checking the proportionality of the corresponding sides by using the angle similarity. Okay, and I know that most of you have realized you've got a few blank spots that you're supposed to fill in, so I'm going to stop for a second. All right, so number 3. Here we have two triangles. The question is whether they are similar or not. What do you think? Are they similar? Yes, they are. And the reason is because of the angle similarity. In fact, I will show you that they are similar. Here I have this. I'm going to start with the smaller one. If I rotate it and then dilate it, you can clearly see that one maps on top of the other. So yes, they are by the angle similarity or by AA. All right, how about number 4? I'll let you try that one. The question is, are these two triangles similar to each other? In this situation, sometimes we've got to find that third angle. So if you find the third angle using the triangle sum theorem, you should realize that this angle right here is, hold on a second, I'm trying to zoom in here. So 64 and 66, that's 130. This angle right here is 50 degrees. And 66 and 50, that's 114 degrees, or 116 degrees, excuse me. And so that would make this angle 64 degrees. Now we can clearly see, although we could have stopped after I found this angle right here, because then we would see that we've got some sort of angle-angle similarity right there. And once again, like in the previous one, I'm going to show you, rotate and dilate, and one maps right on top of the other. That's further proof that yes, these two triangles are similar to each other. All right, so the reasoning is because of the angle-angle similarity. All right, so I want all of you right now to try number 5, 6, 7, and 8. We'll shoulder partner what we have, and then we'll go through those. Go ahead and do 5, 6, 7, and 8. Number 5. Are the triangles similar? Yes or no? No, they're not. If we found the missing angle within each triangle, it would become very clear, because you have to, at least in this situation, think about that. Because right now, the angles that line up here, those two are the same, but I don't know anything about those two or those two. But if I quickly find them, I can see that that's not going to be the case. If I found that one right there, that's 37 degrees. So you can clearly see that these are not similar to each other. And I can show you by scaling one up or down. So if I take that one and translate it and then scale it or dilate it, you can clearly see those are not similar to each other. Or mathematically, we can prove it. So those two are not. Number 6, are these two similar? Yes or no? Same sort of idea there. If I find the third angle within each one, I can clearly see that these are not going to be similar. And then I can also show you by translating and then dilating, and we can clearly see while it's close, they are not. All right. And then the two where you had to do a little more thinking, in my opinion, number 7 here. Are these two similar, yes or no?
Yes.
Yeah, and when I walked around, a few of you at first were having a little bit of a problem with this one, but look, we see that the two 42-degree angles are congruent to each other, but we also have vertical angles right here. So that means this angle is congruent to this one. So now, by angle-angle, I have that angle congruent to that one, and this one congruent to that one. By angle-angle, they are similar. But I also could show you with transformations. So if I take that top triangle and rotate it and then dilate it, we can see that they are similar to each other. And then number 8, really a similar situation here. Are these two similar, yes or no?
Yes.
Yes, they are. And let me show you by angle-angle. The key piece of information here is the fact that line L, or line segment L, is parallel to line segment M. So what happens is we have corresponding angles right here. This angle is congruent to this one. But if I were to split these up, this angle right here is congruent to itself. Or if you didn't see that, we would also have corresponding angles on the other side. But regardless of that, we have similar triangles here because of the angle-angle similarity. And I could just dilate the top triangle to show you that it becomes or lays right on top of the other one. All right, so the last topic for today is extending something from 7th grade, and something that I did talk about, I think it was probably about a week and a half ago. So we have a little bit of background knowledge here. If I tell you that these two triangles are similar to each other, that means one is a dilated version of the other. And we can use the idea of proportional relationships to find that missing side. So when I lay this out, 12, which is to 8, as 10 is to x. Now if you're going to set up a proportional relationship for this, you need to make sure that 12 lines up with 10 right there, and 8 lines up with x. Yes.
Our notes are a lot different.
That's because this one's not in your notes.
Oh.
Yeah, the next one's going to be in your notes, and I'm going to have you find the missing side. All I'm trying to do here is quickly review that by using proportions to find the missing side so that we now truly have similar figures, and that missing side would be 6 2/3. And so we could check to make sure of that by testing the proportionality of the corresponding sides like we've done in other types of problems, and that would prove that they truly are similar. So let's do a little practice of one. Could I get everybody to find the missing side there so that we can then go on? 4 different ways of setting up the proportions, but I'm going to set it up as 12 over 10 equals 15 over x. Some of you have 12 over 15 equals 10 over x. That'll work. 15 over 12 equals x over 10. That will work. But regardless, we should certainly get something bigger than 10, and in fact we do. It's 12 and a half. And once again, we could show that the corresponding sides are proportional like we did in previous problems, but we don't necessarily need to. So I wanted to quickly review this so we could do real-life problems like, and this is a classic example right here, comparing somebody's height to a tree height and the tree shadow to the person's shadow to try and figure out how tall the tree is. And when you're thinking about something like this, in some respect, you're thinking about similar triangles. So in this situation, it's much like the previous problem. And we could use the idea of a proportional relationship to find that the tree ends up being 30 feet tall. And I'm just showing you that there are 4 different proportions that you could use. I'm going to go ahead and solve it from this one, and I get that the tree is 30 feet tall. So now let's go to number 10. And in number 10, we have a similar situation. A 30-foot, or a building that's 30 feet tall casts a shadow that's 75 feet long. A nearby tree casts a shadow that is 35 feet long. How tall is the tree? And I'll let you take it from there. All right, so several different ways of setting up the proportion here. But I have a question for you, and that's this. How do we know the 2 situations lead to similarity? How do we know that? Any ideas? Turn to your shoulder partner and talk about that for a second. How do we know that the 2 situations lead to similarity? We've been talking a lot about transformation. So if I create triangles here and take the tree and the shadow length and I translate it over and I dilate it, I clearly see that we have a situation that leads to a similarity. So getting back to finding the tree height, we could set up a proportional relationship, solve the proportion, and we can see that the tree is 14 feet tall. All right, last problem for today is number 11. Find the missing sides HJ and LK, and you can work with your shoulder partner on this one. We are trying to find the length of HJ, and then we're trying to find the length of LK. All right, to find HJ, lots of ways of doing that. I'm going to use the idea of a proportional relationship. 3 is to 12 as 5 is to x, and when we solve for the missing side there, we get 20. So that one was correct. LK, lots of ways of doing that. I'm going to use the proportional relationship between the whole side, and I'm going to take really the same approach that I took for, if you want to think of that as the hypotenuse, as I did for the hypotenuse. So 3 is to 12 as 4 is to y, and when I find that, I end up with 16. But 16 is the whole thing. And so when some of you did that, that's what you did, but I'm not asking you for HK, I'm asking you for LK. HL is 4, which means LK has to be 12. Okay? All right, we are finished for today.